means a lot of things to a lot of people. In physics, work has a specific meaning. Work is equal to force into displacement. When I want to move an object, I need force, that is work. Whether it is a market or sending a rocket to the space, all requires energy, that is work. How much gas, which possesses stored chemical energy, you need to drive a car from one place to another place, again a work. How much energy do you need to keep this manufacturing plant to be in operation, that is also work. That is what is the work energy theorem helps us to figure out. Work energy theorem. Work energy theorem. The relationship between the work and kinetic energy of the object is called the work energy theorem. It states that the net work done on the system is equal to the change in kinetic energy of the system. That is, the net work done W net is equal to change in kinetic energy delta K. So this is what is telling us the work energy theorem. We shall prove the work energy theorem for the variable force. To do that, let us consider the object acted by the variable force. Over here, the example is going to be the person who is skating. While skating, because of the less frictional force between the ground and the skateboard, we will have continuous decrease or increase in the force. That means that here whatever the force is going to act, that is going to be a variable force. Then work done by the variable force is given by work done is equal to, I wanted to know the total work done of the variable force. Suppose if it is going to start from the point, or it is going to start from the initial position as xi and final position as xf, then my total work done will be force into what is the displacement done by the object. Now the kinetic energy at any instant will be given by, we know the formula for the kinetic energy. So the kinetic energy is going to be given by the formula half mv square, where we have the K as the kinetic energy over here. Suppose if I'm finding the rate of change of kinetic energy, then I should write this as dk over dt. With time, how the kinetic energy is going to vary. So dk divided by dt into, I'll be having that as half mv square, where here the half is going to be constant and m is also going to remain constant, so that my dk will be given by dk divided by dt is equal to m into dv divided by dt into v. Correct? Now we know this from the second law of Newton, that F is equal to ma, or the a is going to be given by dv divided by dt. That means that the m into dv by dt can be replaced by F. So what I'll be having over here now is nothing but dk by dt is equal to dk divided by dt is equal to F into V. Here the V can be further written as F into change in displacement divided by change in time. Now if you are going to find out the values over here, dk by dt is equal to F into dx by dt, or it can be written as dk is equal to F into dx, right? We found this relation dk is equal to F into dx. So by integrating this relation, we can get that integral of dk is equal to integral of F into dx, where the dx is going to have the limit of the initial position xi to xf. Same way here it is going to be the initial kinetic energy minus final kinetic energy. So when we are trying to integrate, we will be getting the answer for this as k, and which will be substituted with the limit of ki to kf, that is equal to, we will be having here that as integral of xi to xf F into dx. Here we know this force into displacement is nothing but work done. So that what we get over here is nothing but change in kinetic energy. Final kinetic energy minus initial kinetic energy is equal to work done. So for a variable force, the work energy theorem is going to be given by the same equation like the constant force. In a nutshell, every object situated at some height with a possibility to come back on the ground has energy stored in it. This energy is called so because it has potential to be converted into some other form of energy. This form of energy can be converted into kinetic energy, mechanical energy, heat and light energy, etc. The potential energy is of three different types. They are nothing but elastic potential energy, as you are seeing it over here in the case of the spring, and gravitational potential energy as the object which is going to be at a height from the ground. Then the third type is nothing but the chemical potential energy, like what is the food and the fuels for the vehicles what we are having, all of them will be coming under the chemical potential energy. That is, in this the energy is stored inside the material as the chemical. In the elastic potential energy, the energy is stored inside the elastic materials in terms of the compressions or the elongation. Now we are going to focus on the gravitational potential energy over here. We all know that Earth is having a gravitational force that pulls object towards the surface. This constant attraction between the Earth and the object leads to gravitational potential energy. This form of energy depends on the mass of the object, height of the object, as well as the amount of gravitational pull of the object. the greater the mass will be the gravitational potential energy. Similar is the case with the height. An object at a higher elevation, as you are seeing here like the rock, will have greater gravitational energy stored in it. So an object is going to lie on the surface of the earth at point A. Here g is the acceleration due to gravity on the earth's surface, and the force of attraction towards the center of the earth is given by the weight of the object, which is going to be mg, mass of the object into gravitational pull. If you wanted to move this object to a point B over here on the earth's surface from point A, then the force that equals to mg has to be applied in the upward direction. The amount of work done by the object at height h shall be mgh. This is also the gravitational potential energy stored in the object at height h. Therefore, the gravitational potential energy will be given by the formula V is equal to mgh, where the value of the g is equal to 9.8 Newton per kilogram. It is essential to know that the gravitational potential energy solely depends on the displacement of the object from an initial height to the final height. We are going to take this object A from the surface of the earth to a height h, and it's going to reach the point B. The amount of work done by the object at the height h can also be written as mgh. This is also the gravitational potential energy stored in the object at the height h. Therefore, we can write this work done as potential energy V is equal to mgh. It is essential to know that the gravitational potential energy solely depends on the displacement of the object from an initial height to the final height. Now, if the object moves upwards to the height h, then the gravitational force acting on the object is negative. So, here the h should be taken as negative, as it's moving away from the earth's surface. Therefore, the force is going to be given by minus mg. Or we can say that as change in potential energy. That means that F is equal to minus of change in height of the object is going to vary the potential energy over here, so that minus d of dh into vh must be equal to mg. The negative sign here denotes that as the object is moving upward, the gravitational force is pulling it towards the downward. The kinematic relation here comes into play and is denoted by the change in speed when the object falls back to the ground. Here, the speed of this falling object increases as it's being pulled by the gravity. Hence, we can write v square minus u square is equal to 2gh, where our u is going to be 0, as at the maximum height it will be 0. That's the starting point, and it's going to come towards the downward. That means that our velocity over here becomes v square is equal to 2gh. Or we can write this as half mv square is equal to mgh. That means that this 2 will go as a multiplication, this m and m will get cancelled, so that we will get the same equation. So both the equation gives us the same meaning over here. Now energy as the negative constraint. This denotes that the potential energy of the object m at a height h converts into kinetic energy as soon as it falls on the ground, as the force acting on the object situated at a height is against the gravitational force from the earth. The potential energy in the object behaves as the negative constraint now. But this energy by virtue of height becomes a positive constraint as soon as the object reverts to the ground. The potential energy V further for the f of x can be written as integral of f of x into dx is equal to minus integral of v into dv. That gives us, by integrating, vi minus vf, where we know that here f of x is equal to minus dv by dx, where here we know that f of x is equal to minus dv divided by dx. So what is the final equation we are going to have here? By taking vi as the initial value of the potential and vf is the final value of the potential. The distance between the 2 points is irrelevant here, as gravity depends only on the initial and the final positions. So that here, what is this vi minus vf we have? That can be written as delta v. That is going to be equal to minus of f of x dx. From this relation we have got our final answer. So the change in potential energy is going to be given by the work done, that is force into displacement. The dimension of the potential energy are the same as the normal energy. So the dimensional formula, if you are trying to write for the potential energy, that is going to be given by, what is the formula? mgh. So for m you will be writing that as kilogram, for g it will be meter per second square, and for h it's going to be meter. So the dimensional formula is going to be given by, for kg it is going to be m power 1, for L the meter squared L power 2, for T second power minus 2. So the potential energy is going to have the dimensional formula as m1 L power 2 T power minus 2, and the unit for that is joule as of the kinetic energy and the work done. To reiterate the change in potential energy for the conservative force, delta V is equal to the negative of the work done by the force. 6.8 Conservation of mechanical energy. When we are trying to talk about the conservation of mechanical energy, we must know about the conservative force and the non-conservative force. So when we are trying to talk about the conservative forces do no net work done over a closed loop. That is, they do equal work between 2 points irrespective of the path. That is, from the point A to B, if the object wants to move, that is going to do the same amount of work. Whatever the path it follows, that won't affect the net work done. For example, kinetic energy is conserved on returning to the same position each time. But when it's going to come for the non-conservative force do net work done on a closed loop. Like A to B is going to be a closed loop. It will do a net work done. That is, it will do more work over longer distances. So it's path dependent. The kinetic energy is not lost on returning to the same position each time. In the conservative force, the kinetic energy is going to lose by the object as it's taking a longer path in the non-conservative force. So in the conservation of mechanical energy, we are going to consider an object which is going to be supplied with the conservative force. So as a result of the conservative force, the object is going to have the change in energy of that, which can be written as the change in kinetic energy of that can be given by f of x into del x according to the work energy theorem. If this force is conservative, that means that the potential energy of this over here can be defined as, because in a conservative force the potential energy is going to be negative of the work what has been done over there. So we will be having the potential of that over here as, instead of kinetic energy, potential energy we are going to write. So that will be given by minus delta V is equal to f of x into del x. So this is according to the conservative force what has been supplied. Yes. Now the above equation implies as that is the total energy of the system remains constant always. We know that. What is the total energy? That is total kinetic energy plus total potential energy must be equal to 0. There should not be any change in it. Correct? So if I am taking the del out, I will be having that as k plus V is equal to 0. That is, the total change in the energy is going to be 0, or we can say that the total energy remain constant. So if the object is going to move from the point xi to xf, from the A to B we are saying here, right? So let that take that as xi to xf. If it is going to move, then the total energy associated with that can be given by initial kinetic energy plus initial potential energy, that is V of xi, must be equal to final kinetic energy plus final potential energy xf, right? Now here the quantity k plus V of x is called as the total mechanical energy of the system. We have done the individual total energy before and after. Both of them are going to be equal to each other, right? So by recapitulating, we can give the definition for the conservative force as a force f of x will be conservative if it can be derived from a scalar quantity V of x by the relation given by the above equation what we have over here or over here. So the work done by the conservative force will be given by, work done is equal to either it is going to be change in kinetic energy or it will be given by change in potential energy. When you are writing potential energy, there will be a negative sign because initially it will be more and finally it will be less. So V of xf minus V of xi, if you are writing, because of the minus sign, this equation will be changed into V of xi minus V of xf. So if there is conservative force is going to act on the system, the work done of that will be given by final kinetic energy minus initial kinetic energy, or the work done will be given in terms of the potential energy as initial potential energy minus final potential energy, right? So basically, as it's a conservative force, the work done is going to depend upon the initial and the final position only, not the path over here. So the total mechanical energy of the system is conserved if the forces doing work on it are conservative. That is, if the force acting on that is going to be non-path dependent, it will be conservative. So let us discuss about an example over here when we are talking about the conservative force over here. So I'm going to have a mass which is going to act on the x and y axis over here. So along the x axis I have written it over here, and I'm going to have this mass which is going to be placed from the origin over here like this, where we are going to consider three different points over here. The first point is going to be the highest point over here, which is going to be given by v equal to 0. That is, the velocity of that at the maximum point is going to be 0. And in middle, any one of the point I'm going to consider, where the velocity of that is going to be considered as v0. Then the final position, the v value is going to be vf. Now from the down, what is the height at which this object is in the middle part, that we are taking that as h here. That means that the overall height should be something else, as I have taken that as small h. So the overall height over here is going to be capital H. So the conservation of potential and the mechanical energy, we are going to look at it. We are considering a ball over here which is going to have the potential energy of it at the maximum height as potential energy at the height, or the total energy at the maximum height. The object will be at rest, so the potential energy only it will be holding, no kinetic energy. It is for the first height, that is at this point v equal to 0, what we have now. There the total energy is going to be mgh alone, because the ball is at rest, so no kinetic energy, only the potential energy. When we are trying to find the total energy at this second point, let us name them A, B, C. So I'm finding the total energy at the point B now. So my point B is going to be at the height of H. So it's going to be given by EH. EH will be given by, I have to write both total energy, that is kinetic and potential energy plus kinetic energy. So mg small h plus half m vh square, or v naught squared is the one what I have written over here. So this is going to be my second equation. When we are coming for the third point at C, if you are going to have, this is at A and this is at B and this is at C, I'm going to have at C the object will be in motion, right, as it hits the ground. So at that point the energy of that is going to be given by kinetic energy half m vf square, because vf is the velocity what I have taken over there, right? And when we are trying to get the formula for the conservative force over here, that is the energy is conserved all over this part. So at A, B, C, all these points the energy should be conserved. So if I'm taking in that way, EH must be equal to E0, am I correct? And EH must be equal to E small h also. So we are going to take it one by one and we are going to prove it. So I'm going to take the first case over here. The first case can be given by, what is the first case we are considering here? EH is equal to E small h. So that what I'm going to have as a result of that is nothing but E capital H is going to be mgh, that is equal to E small h is going to be mgh plus half mv0 square, where m is common all around it, so it will get cancelled. and we don't have the G over here. So the G, if I want to cancel from all of them, let us multiply and divide the G over here. So the multiplied G will get cancelled. So what is the rest I will be having here is nothing but I'm just writing that equation here down. H is equal to H plus 1 by 2G into V naught square, or capital H minus small h is equal to V naught square divided by 2G, or V naught square is equal to 2G into capital H minus small h, right? So this is my intermediate velocity, what it is going to have over here. At the same time, if I'm trying to do that as EH is equal to E0. What is the EH value? mgh. What is the E0 value? Half mvf square, where this m and m will get cancelled, the 2 will go on the other side. So vf square is equal to 2gh, or vf is equal to root of 2gh. So this is how the energy conserved at all the points is being proved, and we got the velocities according to the different positions as well. That means that at the height capital H, the energy is purely potential. It is partially converted into kinetic energy at the height small h, and is full of kinetic when it is at the ground level. This illustrates the conservation of mechanical energy over here.